All right, hey guys, we're going to start off by looking at chapter 5. So we'll start with these true or false questions. So the first one says, a charged object can have any numerical value as its charge. This is false because charge is quantized. You can only have an integer number times the charge of a proton if it's positive, or the charge of an electron if it's negative. You can't have any arbitrary value as a charge. 2, electrons are positively charged. This is false. Electrons are negatively charged. 3, if 2 insulators are charged via friction by rubbing them together, then the positively charged object stripped off some protons of the negatively charged object. This is false. Only electrons can be transferred between objects composed of atomic matter, at least. The protons are held pretty firmly in place, but if you rub vigorously enough, then you can cause some transfer of electrons. 4, a conductor is charged via conduction with a negatively charged insulator. The conductor is left negatively charged. This is true. So remember, if you charge something by conduction, then you have some whatever negatively charged object here. If you touch that to your conductor, these are supposed to be touching, and the electrons actually jump off of the insulator and they go onto the conductor. And so when you pull the rod away, you're left with some negatively charged conductor. All right. A conductor is charged via induction with a negatively charged insulator in the help of the ground. The conductor is left negatively charged. This is false. When you charge something via induction, you end up with the opposite sign charge. Let's delete this. So this time, you have some negatively charged insulator. If you hold it close to a conductor, well, the electrons over here are going to put force on the free electrons that can move around in the conductor, and you'll be left with this part negative and this part positive. You then want to ground this side, either by touching it with your finger or touching it with something, whatever. In some way, you connect this to the ground. This is usually the symbol for the ground. So all of these positive charges over here want to stay, but all these negative charges over here want to go. So these electrons are going to go into the ground. And so then you'll be left with some positive charge on this side. So you remove the ground and then you remove the rod. Once you remove the rod, the charge distributes itself evenly, and you're left with a positively charged conductor. Okay. A negative and positive charge are separated by some small distance. This is necessarily an electric dipole. Not necessarily. To have a dipole, the positive and negative charge have to have the same magnitude. This just says that we have a positive and negative charge, not their relative magnitudes. 7, a point charge produces an electric field which is constant over spheres centered at the point charge. This is true. So if you have a point charge, the electric field for the point charge are these constants times the magnitude of the charge, or times the sign charge divided by the distance squared in the r hat direction. So this only depends on the distance away. So if you draw a sphere centered at the point charge, the electric field is constant over that. You can draw as many spheres as you want. The electric field is always going to be constant over that sphere. All right, one more. If a sphere of radius 0.25 meters has a constant surface charge density of 10 microcoulombs, that should be per meter squared, it has a total charge of about 30 microcoulombs. So the meter squared should actually be over here, my bad. So no, this is false. If you know sigma, you know the charge density. This, remember, is the charge per area. So to find the total charge, you multiply by the area. So we have a sphere here. So we multiply by 4 pi r squared. And with these values, that does not give you 30. Okay. So short answer questions. Draw the electric field lines for a single positive charge, a single negative charge, a dipole, and two finite plates such that one is positively charged and the other is negatively charged, but with the same magnitude of total charge. Okay. Well, if we have just a single positive charge, then the electric field points radially out. So the field lines look like this. They point away in all directions. And if this was in full 3D, there would also be some coming out of the screen on this side, going into the screen on the other side, etc. For a negative charge, it's the same, but the opposite sign. So the electric field points radially inward. All right. If you have a dipole, then you have a positive and negative charge of equal magnitude, meaning that total you have zero charge, you have zero net charge here, which means all of the field lines that start here have to end here. So that looks something like this. So the point is that all of these lines that start over here have to ultimately end at this negative charge. And finally, the parallel plates, we've drawn this one a whole bunch of times. So I'll just draw it like in 1D. So here's our positive plate. Here's our negative plate. We know that it's straight in the middle. And the farther you get away from the middle, the more sort of curved it is. But we have a similar situation here where we have equal amounts of positive charge and negative charge. So all of the field lines start here and have to end here. All right. So suppose a positively charged rod is brought close to a spherical conductor. Sketch what happens to the conductor, including what, if anything, happens to the charges which compose the conductor. All right. So if we have a positively charged rod and we bring it close to a spherical conductor, well, there's lots of free electrons that can move around in here. And so they're all going to be drawn toward this positive rod, which will leave this other side positively charged. So the important thing to note here is that the electrons, which are more or less evenly distributed before, have all moved to this side. And so if we had a negative charge, then it would be the electrons that move to the other side. The point is that it's always the electrons that move, never the protons. Okay. A 1 microcoulomb charge is located at the origin, and a negative 1 microcoulomb charge is located at the point 1, 0. What is the magnitude and direction of the force on each charge? All right, so we have a 1 microcoulomb charge over here, a negative 1 microcoulomb charge over here. Well, because these have opposite signs, they're going to be attracted to one another. And so maybe we'll call this one Q1 and this one Q2. So this is F21, the force on charge 1 due to charge 2. And this is force 1, 2, the force on charge 2 due to charge 1. Now, because of Newton's third law, they have the exact same magnitude. So the magnitude of F21 is the same as the magnitude of F12. And that's 1 over 4 pi epsilon naught times the absolute value of the charges divided by the distance squared. So in our case, this distance here is 1 meter. So these are numbers, we know what they are. Then we multiply by the absolute value of each charge. So this is 1 microcoulomb and this is negative 1 microcoulomb. So we have 1 times 10 to the minus 6 coulombs squared, because after you take the absolute value, these have the same value. And we divide by 1 meter squared. And so if you evaluate this, this is going to be 0.0090 newtons. But we were asked not just for the magnitude, but also for the direction. Well, for F21, we can see this is going in the positive x direction. So it's positive 0.0090 newtons in the x direction. And F12 is always going to be negative what this one is because of Newton's third law. Or we could have seen that just from the way that we drew the picture here. Okay. Electric fields and the electrostatic force obey the superposition principle. What does this mean? The superposition principle just means if you have multiple sources, so this could be multiple point charges or multiple distributions or whatever, you just add all of their contributions together. So it's the easiest to see for point charges. Oops. If you've got a whole bunch of point charges and maybe you want to know the electric field here, well, that's just the total electric field is the electric field due to charge 1 plus the electric field due to charge 2 plus the electric field due to charge 3 plus however many charges you have. And the force obeys the exact same thing. So for instance, the force on charge 3 is the force due to 1 plus the force due to 2. And if you had more charges, you would just keep adding forces. All right. If a charge Q is placed in electric field E, what is the force on this charge? So if we have some electric field that already exists independently of our charge, maybe it looks like this. This is our electric field. And we have some charge Q that's inside of it. The force on it is the charge times the electric field. Remember, this is how we define the electric field in the first place, to be the force per charge. So if we invert that, the force on a charge is the charge times the electric field. So if our charge is positive, the force points in the direction of the electric field. And if our charge is negative, then it points against, the force points against the electric field. So if this was an electron, it would go this way. If it was a proton, it would go this way. All right. If a conductor in electrostatic equilibrium is charged, how is the charge distributed in the conductor? It's always only on the surface, and it's more concentrated in places where the radius of curvature is less. So we did this in class today. If you have some whatever weirdly shaped conductor, there's going to be a lot of charge in places where there's a tiny radius of curvature, and then kind of less charge in places where there's not. Okay, but no matter what, it's only ever on the surface. All right, two charges exist in otherwise empty space, Q1 and Q2. The force F12 is 1/4 pi epsilon naught Q12, Q1 times Q2 divided by R12 squared times R12 hat. Describe in words what R12 and R12 hat are. Okay. So we have two charges, Q1 and we have Q2, and we're looking for, what were we looking for? F12? Yeah. So F12 is the force on charge 2 due to charge 1. So R12 is just the distance between them. So just whatever this physical distance is. And R12 hat is the unit vector that points from Q1 to Q2. is the unit vector. So the full R12 vector points from Q1 all the way to Q2. And to make it a unit vector, you just divide by the distance. Okay, so we always use the vector that points from whatever's creating the force to wherever we want to know the force. And if we wanted the electric field instead, say we want the electric field due to some charge here, then we use the vector that points from the charge to the point where we want to know it. So that would be the full vector. And then the unit vector would be just dividing by the magnitude. Sorry. All right, long answer questions. Three charges lie in a plane with Q1 equal to 1.5 microcoulombs at the origin, Q2 equals negative 2.7 microcoulombs located at 1.50, and Q3 is negative 3.3 microcoulombs located at negative 0.27, negative 0.13. All right, so anytime you want to do a problem like this, the first thing you should do is draw a picture that shows where all of the charges are. So in our case, each of these ticks are 1 meter. So Q1 was at the origin. That's Q1. No, draw it in red. Q2 was at 1.50. So that's Q2. And Q3 was at negative 2.7.13. So that's up here. Okay, and we want to know the force on charge 1. Well, the total force on charge 1 is the force on charge 1 due to charge 2 plus the force on charge 1 due to charge 3. So in other words, we only look at these 2 at a time and calculate the force, and then we add those together. So let's first find F21. Well, F21 are these constants times the product of the charges divided by the distance squared times the unit vector that points from the one creating the force to the one where we want to know the force. Okay, so we can completely ignore 3 here. This is only about 1 and 2. All right, so what do we do to get from charge 2 to charge 1? So let's just redraw this here. Here's Q1. Here's Q2. Now the full vector points from what's creating the force to where we want to know the force. This is our full R21 vector. To find the unit vector, R21 hat, we just divide by the distance here. Now, normally this would be a triangle, but we just have a straight line just because they're both on the x-axis. And so to go from Q2 to Q1, we clearly have to go in the negative x direction. And Q2 was at 1.5 meters. So we have to go negative 1.5 meters in the x direction. So our full vector, R21, is negative 1.5 meters in the x direction. Okay. Well, we can find the distance by taking the square root of the sum of the squares. But here we only have an x distance. We don't have a y one. So the distance we can tell right away is just 1.5 meters. So we can find our unit vector, R21 hat, by taking our full vector and dividing by the length or the magnitude. So negative 1.5 over 1.5 is just 1. And remember, unit vectors, sorry, negative 1. Unit vectors never have units. The units divide away when you divide by the magnitude. So our unit vector here is negative 1 in the x direction. Okay, so we have everything that we need now. Our force is this constant times the charge of 1. The charge of 1 was 1.5 microcoulombs. That's 1.5 times 10 to the minus 6 coulombs. Our charge 2 was negative 2.7 microcoulombs. That's negative 2.7 times 10 to the minus 6 coulombs. Then we divide by the distance squared. Our distance is 1.5 meters. And then we multiply by our unit vector. So let me move this out of the way. Ooh. All right, I don't know how to do that. We multiply this by our unit vector, which is negative 1 in the x direction. All right, so the result of doing this is 0.016 newtons in the x direction. Now, every time you do this, you should ask yourself, does this make sense? So this is telling us that the force on charge 1 due to charge 2 is in the positive x direction. Well, our forces are separated like this. Q1 is positive and Q1 is negative. So the force should be attractive. So Q1 should be being pulled toward Q2. That is the positive x direction. So this does indeed make sense. All right, so now we need to find F31, the force on charge 1 due to charge 3. So let's draw these positions of our charges. Well, Q3 was up here and Q1 was down here. Now remember, the vector that points from what's creating the force to where we want to know the force is our full vector R31. So you have to ask yourself, what do I have to do if I'm at Q3 and I want to get to Q1? Well, I have to go some distance in the negative y direction and then some distance in the positive x direction. So what are these distances? These are the actual difference in the coordinate values of our points. So this will only give you the number, not the direction. You got to figure out the direction for yourself. So we can see that we have to go in the negative y direction and the positive x direction. And so I just subtract the y values of Q3 and Q1 and then make it negative. And that'll be the y part of this. And then I subtract the x values of Q1 and Q2 and make it positive, and that'll be the x part of this. So in our case, Q1 is at the origin, so it's particularly easy. The delta y is just the y coordinate of Q3, and delta x is just the x coordinate of Q3. Okay, you just have to make the signs right. So this means I have to go positive 0.27 meters in the x direction and negative 0.13 meters in the y direction. This is the vector that takes me from 3 to 1. Okay. Now I can find the distance here by finding the magnitude of this. So this is the square root of 0.27 meters squared plus negative 0.13 meters squared. So the result of this calculation is 0.30 meters. And now if I wanted to, I could find the unit vector by just taking this vector and dividing it by 0.3. But I could do something else. And the other thing is slightly easier, so that's what I'm going to do. Now we normally defined F31 like this. But this unit vector here is our full vector divided by this distance. So I can rewrite this by having this distance cubed and then having the full vector here. Now, if this doesn't make sense to you, then just go ahead and take the full vector and divide by the distance. In the end, you'll get the exact same expression. All right. So our F31 then are these constants that we don't care about times Q1 Well, Q1 was 1.5 times 10 to the minus 6 coulombs times Q3. Well, Q3 was negative 3.3 times 10 to the minus 6 coulombs divided by the distance cubed now. Well, we just calculated the distance was 0.30 meters. And then now we multiply by the whole vector here. All right, well, we found the vector was 0.27 meters in the x direction and negative 0.13 meters in the y direction. So our full force then is this stuff times this for the x direction. So that'll give us negative 0.45 newtons in the x direction. And then this stuff with the constants times this for our y direction. So this is plus 0.21 newtons in the y direction. All right, so I got my number here. Let's go up and make sure that it makes sense. These things have opposite signs, which means that Q1 should be attracted to Q3. That means it has to go in the negative x direction and the positive y direction. Well, that's exactly what we got here. We got negative x, positive y. Now, what we actually are after is the full force on charge 1, which remember was the force due to 2 plus the force due to 3. So we just add the x parts of these two together, and that'll be the full force in the x direction. And then we add the y parts, and that'll be the full force in the y direction. Okay. So if you actually do that, remember F21 only had an x direction. So we'll get negative 0.43 newtons in the x direction, and the same plus 0.21 newtons in the y direction. All right, so next we're asked to find the electric field at the point 1.7, 1.7. Okay, so let's redraw our problem here. All right, so Q1 was at the origin. Q2 was some distance over here. Q3 was over here. And we want to know the electric field at 1.7, 1.7. So that's slightly past Q2 and then up some. So here's our point P, it's a P. This is where we want to know the electric field. All right, well, the total electric field is the electric field due to charge 1 plus the electric field due to charge 2 plus the electric field due to charge 3. Okay, so just like we did with the force, we'll take these one at a time. So also, I won't do charge 3. It works the exact same way as charges 1 and 2. So we'll just pretend like charge 3 doesn't exist for this part. Okay, so let's start with the electric field due to charge 1. All right, so it's always best to go ahead and draw your charge and your point where you want to know the field. Now here, this is the full vector R1. Remember, our vectors always point from what's creating the force or what's creating the field to where we want to know the force or where we want to know the field. In this case, we're dealing with the field. So our vector points from the charge creating the field to where we want to know it. Okay, so this is the full vector. And we can break this up into a triangle. And so we have some part in the x direction and some part in the y direction. Just like we did with the forces, this component is going to be delta x, and this component is going to be delta y. And we can see if we actually wanted to walk from Q1 to the point P, we'd have to go in the positive x direction and the positive y direction. So we just subtract these things, subtract the x components of Q1 and P, make it positive, that'll be the x part of R1. Subtract the y components, make it positive, that'll be the y part of R1. So now our point is at 1.7, 1.7, and our Q1 is at the origin. So this is really easy. Our vector is 1.7 meters in the X direction plus 1.7 meters in the Y direction. All right, easy enough. Now we can find the distance between Q1 and our point P by taking the magnitude of this vector. This is 1.7 meters squared plus 1.7 meters squared. So the result of this is 2.4 meters. So this is the distance between Q1 and our point P. Now, if we wanted to, we could divide these and find the unit vector, but I'd rather not. So normally we said that the electric field due to a point charge is defined as 1 over 4 pi epsilon naught times the charge divided by the distance squared, say 1, times the unit vector. But the unit vector is the full vector divided by the distance. So this is the same as the distance cubed times the full vector. Okay, this just saves one step in the calculation. If it confuses you, just go ahead and do it. It doesn't really matter. All right, so our electric field here are these constants times the charge of charge 1. That was positive 1.5 times 10 to the minus 6 coulombs divided by the distance cubed. So that's 2.4 meters cubed. Now times that full vector that we just found. We found it to be 1.7 in the X and 1.7 in the Y. Okay. So because of the symmetry here, this is going to be the same in the X and the Y, but in general, that won't be the case. So if you calculate this, the electric field is 1,660 newtons per coulomb in the X direction, plus 1,660 newtons per coulomb in the Y direction. All right, so let's do 2 now. All right, so we want to do the electric field due to 2. Well, we do the same thing. We draw our Q2, we draw our point P. And so the vector that points from the charge to where we want to know the field, that's our full vector. And we split it up into a triangle. Whose sides are the distance in the X components, or the difference in the X components and the difference in the Y components. And we can see if we wanted to walk from Q2 to the point P, we'd have to go in positive X direction and the positive Y direction. Okay. So if we subtract the X values of P and Q2, then what we get is 0.2 meters. So we wanted to make this positive because we need to go in the positive X direction. So positive 0.2 meters in the X. And the result of subtracting the Y parts is 1.7. That needs to be positive as well. All right, so this is our full vector. We can calculate the distance like we normally do. It's 0.2 meters squared plus 1.7 meters squared. So this is 1.7 meters. The reason why it's the same is because 0.2 is so much smaller than 1.7. Okay, so anyway, our electric field due to charge 2 is 1 over 4 pi epsilon naught times the charge 2 divided by the distance squared times the unit vector. Or if you don't feel like calculating the unit vector, we can just change this to cubed and use the full vector. All right. Our Q2 was negative 2.7 times 10 to the minus 6 coulombs. Our distance was 1.7 meters. So we cubed that, and then we multiplied by the full vector. All right, so Sorry, my internet cut out or something. So the result of doing this calculation is that you get negative 990 newtons per coulomb in the x direction and negative 8,400 newtons per coulomb in the y direction. Now, we didn't do this for the first electric field, but we should have. We should see if this makes sense. So remember, the electric field points in the direction of the force on a positive charge. So if we put a positive charge at the point P, it would be attracted to the point Q, which means that it would want, the force would go in this direction, which is in the negative X and the negative Y. Well, our electric field has a negative X component and a negative Y, so that's all good. All right, now, like I said, I'm just going to ignore charge 3 because it works exactly the same way and it's a long calculation. So if we're ignoring our charge 3, our total electric field is E1 plus E2. So we add the X parts together and we add the Y parts together. So if you do that, you'll find that the total electric field is 670 newtons per coulomb in the X direction minus 6,800 newtons per coulomb in the Y direction. Okay, so the last part of this question says, if an electron is placed at this point P that we've been talking about, what is the force on it and what is its acceleration? Okay, well, if we know the electric field at some point, like we do, we know our electric field at P, the force on a charge Q that's placed at that point is Q times the electric field at our point. So in other words, we take our vector up here and we multiply by the charge of an electron. The charge of an electron is negative 1.6 times 10 to the minus 19, which is given in the problem. And so we just multiply that by the X and that by the Y. And what we get is that the force is negative 1.1 times 10 to the negative 16 newtons in the X direction and negative 1.1 times 10 to the negative 15 newtons in the Y direction. Okay, now we also want to know the acceleration. Well, the net force on an object, as far as we know, this is the only force in the acceleration, or on the electron. So our force is equal to mass times acceleration. So the acceleration is the force divided by the mass. So you just take this vector and divide by the mass of an electron. And we'll see that the acceleration is negative 1.2 times 10 to the 14 meters per second squared in the X direction, plus, sorry, this should have been plus, because the charge of an electron is negative, so it switches the sign, plus 1.2 times 10 to the 15 meters per second squared in the Y direction. All right. So these problems are really long and tedious, but they're really easy. Okay. So the next two are the exact opposite. They're fairly short, but they're a little bit harder. All right, so we have a line charge with constant linear density lambda. It has a length L, and we want to know the electric field height Z over the left end of the line charge. All right, so let me draw the charge in blue. We have some line charge here, and we want to know the electric field over the left end, some height Z. This distance is L, and it has a constant lambda. All right, so in general, the electric field due to a linear charge distribution is 1 over 4 pi epsilon naught times the integral of lambda dl over r squared times this unit vector. So DL is the actual length of a little piece here. So let's say this is along the X direction. In fact, let's call this point X equals 0. So this point then is the point X is equal to L. And this distance is just dx. Okay. Now this vector r hat here is the unit vector that points from an arbitrary dl somewhere along our line charge to where we want to know the field. So in other words, this is our full vector, and we can divide by the magnitude to find the unit vector. All right, so because we called this point x equals 0, the distance from here to this arbitrary dl here is just the distance x. So this is the distance x. So if I'm at dx at this little place here, and I want to get to where I want to know the field, I have to walk negative x in the x direction, and then up z in the z direction, if this is the z direction. So our full vector r is negative x in the x direction plus z in the z direction. Okay, well, I can also find the distance by taking the square root of the sum of the squares. So in this case, this is going to be x squared plus z squared. Okay, now our unit vector here, r, our hat, is our full vector r divided by r. So when we plug that in here, we're going to have the full vector here and this cubed just like we did before. All right, we can also pull lambda out of the integral because it's a constant. All right, so our electric field then is lambda over 4 pi epsilon naught times the integral over dx of our r, which is this thing cubed. This is already to the 1/2 because of the square root. So this is x squared plus z squared to the 3/2. Then we multiply by our full vector, which was minus x in the x direction and plus z in the z direction. And go back up to our picture here. We're charged everywhere from x equals 0 all the way up to x is equal to L. So we integrate from 0 to L. Okay. So now we can break this up into our x component and our y component, or in our z component rather. So the x component is everything in front of the I hat. So that's a negative x and all of this stuff. So our EX, we still have all these constants here. We have a negative sign from here. Dx over x squared plus z squared to the 3/2. Now, if this was over a symmetric interval, like if this was from minus L over 2 to L over 2, this would automatically be 0 because we have an odd function here, right? But we don't. We're going from 0 to L, so we can't do that. All right, now this integral, I would expect you to be able to do because you can do it easily with u substitution. So if you set u equal to x squared plus z squared, then du is 2x dx. Now we have an x dx up here. So x dx is du over 2. So we can replace our numerator without the negative with du over 2. And we can replace our denominator with u to the 3/2. Okay. So our x component is minus lambda over 4 pi epsilon naught times the integral of 1 over u to the 3/2 times du. Now, if you wanted to, you could figure out what these endpoints are in the u world. Like, so plug in x equal to 0 and see what u is, plug x equal to L, see what u is. Or you could just do the integration and then convert back to x. That's what I prefer to do. All right, so this is an easy integral. You have u to the minus 3/2. That's what 1 over u to the 3/2 is. We add 1, get u to the minus 1/2, and then we divide by negative 1/2 or multiply by negative 2. So this is going to cancel our negative here. And I didn't divide by 2. This is supposed to be an 8 because of this 2 here. So that'll cancel with that and give us a 4 back. So we have lambda over 4 pi epsilon naught times 1 over the square root of u. Well, going back to x and z, this is the square root of x squared plus z squared. Now don't forget to plug your limits in. So this is from x equals 0 to x equals L. Oops. So our full x component of our electric field then is lambda over 4 pi epsilon naught times 1 over the square root of L squared plus z squared minus 1 over z. That's what you get when you plug in 0 for x here. Okay. Now this is always negative, right? This function is always bigger than this function. So that tells us that our electric field in the x direction points in the negative x direction. So let's see if that makes sense. At least assuming that lambda is positive. So we want to know the electric field up here. We have a whole bunch of charge on this side and no charge on this side. So it does seem reasonable that the electric field would point in this direction, as long as we have positive charge here. All right, so this seems reasonable. Now let's go back to the z component of our field. All right, so we still have these constants out front. This time we can factor our z out because we're integrating over x, not z. So z is just a constant relative to x. So I end up with this integral, and this is an integral that you can't do. This is a hard integral. You have to use trig substitution, and it would take you an hour. So if this is on the test, I will give you this integral. And so it turns out that it's equal to this. It's x over z squared, the square root of x squared plus z squared. And then we still have to evaluate it from x equals 0 to x equals L. Okay, well, one of our z's are going to cancel here. So the z component of our electric field is lambda over 4 pi epsilon naught times L over z, the square root of L squared plus z squared. Okay, when we plug in 0 for x, we just get 0. All right, so we have our z component and we have our x component. So we can put them together and find that the total electric field is the x component along the x direction plus the z component along the z direction. And so what is that? There's a lambda over 4 pi epsilon naught in front of everything, so we can pull that out. And then we had this 1 over the square root of L squared plus z squared minus 1 over z. That was our x component. And our z component was this thing. All right, so this is our full electric field over the left end of a finite line charge with constant linear charge density. All right, so the next part asks what? What happens if it extends to infinity? Only on one side. Well, if we send L to infinity, that really is only sending this one part to infinity because we started from 0. So if L changes, we still started at 0. So if we send L to infinity, that's only sending this side out to infinity. And so if we do that, this term goes to 0. This term doesn't have an L, so it doesn't care. What happens to this term? Well, we have an L over the square root of L squared plus Z squared. Well, as L goes to infinity, this Z doesn't matter. And so we have L over L, that cancels. And so we just end up with 1 over Z. Okay, so in the limit that L goes to infinity, our electric field, the constant stayed the same. We get minus 1 over Z in the X direction, plus 1 over Z in the Z direction. Okay, so not too hard. So our next question saying, charge is distributed over a square of side length S and constant surface charge density sigma. What is the electric field at height Z over the center of the square? All right, so we have, let's draw a charge in blue. So we have a charge square here. All of this is charged. I'm not going to sit and fill this in, but you get it. The whole square is charged. Okay, and we want to know the field over the center. So this is our point P where we want to know the field. Okay. Well, in general, the field for a surface charge is 1 over 4 pi epsilon naught integral of sigma dA over r squared r hat. So we need coordinates here, and we should pick good coordinates. So let's call this point in the plane in the middle the origin. In fact, you should always call the point right below where you want to know the electric field the origin. That's always going to be good advice. Okay, so let's call this the X direction and this the Y direction. So if we're smart, we choose X and Y coordinates such that the axes are parallel to one of the sides of the square. By the way, this is the side length S, so is this. Okay, and so dA is the actual area of a little square here. We don't have to pick a square, but this is the smartest thing to pick because we have a square. And so let me draw this again just in 2 dimensions. So I'll just draw it in the XY plane. So here's Y, here's X, Z comes out of the screen. Here's our square here, it's supposed to be centered on the origin. And so a little piece here, well, this, because this is parallel to the x-axis, has length dx, and this, because it's parallel to the y-axis, has length dy. So the area of this little piece here is just dx times dy. And our r vector points from an arbitrary one of these to where we want to know the field, okay? So this little square here is at the point x, y. And so if I want to get from the point x, y back to the origin, then I have to go negative x in the x direction, negative y in the y direction. And then don't forget, I don't want to know the field at the origin, but a height z above it. So I also need to go plus z in the z direction. Okay, so if I write my field again, then I can pull sigma out because it's just a constant. I have to integrate over the area. And then I have to divide by the distance of this. Well, the distance is easy to find. It's the square root of the sum of the squares. So that's x squared plus y squared plus z squared. And in our formula, we wanted the distance squared. But our r hat is this thing divided by this. So I actually have the distance cubed. once again, just like we saw before. So this is x squared plus y squared plus c squared to the 3/2. And I have to multiply by my vector here. This is negative x in the x direction, negative y in the y direction, positive z in the z direction. All right, but I know my dA is dx dy. So I can simplify this. It doesn't matter which one comes first, by the way. The order of integration doesn't matter. At least in physics, it matters sometimes in math, but not very often. Okay, so, well, let's rewrite the rest of this. So we have our vector here. Divided by our distance cubed. Now I need to know what I should integrate from. Should I integrate from what to what? Well, this is a square, so I integrate over where there's charge. There's charge on the interior of the square, so I have to integrate over all of it. And it's centered at the origin and of side length s. That means x has to go from negative s over 2 to s over 2, and the same for y. Okay. Now the x part of this will be just what's in front of the I hat. So we'll have negative x over this stuff integrated over y and x. But that's going to be 0 because the integral over x, this is an odd function over a symmetric interval. So that's going to give me 0. And the same for y when we integrate over y. So there's only going to be a z component. Now we probably would have guessed that anyway, just from the symmetry of the problem. We want the field over the center. So there's equal amounts of charge on either side in the y direction and equal amounts of charge on either side in the x direction. So any x and y part to the field here are going to go away and we'll only have a z. So either one of those explanations is fine with me. Either this is an odd function and we're integrating over a symmetric interval for both x and y, or just from the symmetry, the x and y parts have to go away. So we're only left with a z component. So this is sigma. Now I can also pull this z out because I'm only integrating over x and y. I'm not integrating over z, so z is just a number. This is just the height where we want to know the field. All right, now this is a horrendous integral. I'm not sure I could do this integral if you gave me 6 months. At least not without a computer or a book or something. So if I give you this on the test, I will 100% give you this entire integral, like the double integral version of it. And so what you get if you do that integral though, is you get sigma over pi epsilon naught times the arctan of s squared over 4z square root of s squared over 2 plus z squared. So this is the z component of the electric field, or in other words, the total electric field is this thing. Whoops. In the z direction. All right, now the last part of our problem here, or sorry, the second to last part says, what happens to the electric field if the square extends to infinity? All right, so in other words, I want to take the limit of this thing as s goes to infinity. Both sides of the square have side length s. So if I take the limit as s goes to infinity, that's the same as the square going to infinity. Okay, well, the s is only inside of our arctan. there's an s squared on top and the square root of s squared on the bottom. So the z is not going to matter as s gets really big. When we take the square root, this is just going to be s. This s will cancel with one of these, but we'll still have one in the top. So this is the arctan of infinity. Well, the arctan of infinity is pi over 2. But we also have a z here. So really, this is the arctan. So this thing is like the arctan of the sine of z times infinity. So if the arctan of positive infinity is positive pi over 2, the arctan of negative infinity is negative pi over 2. So this is the sine of z times infinity. So you might have ever seen this before, but the sine of a function just, it's +1 if it's positive, it's -1 if it's negative, and it's 0 if it's 0. Okay, so this is plus or minus pi over 2. Sorry, not infinity. Pi over 2. All right, so this pi over 2 is going to cancel one of these pi's, then we'll have a 2 in the bottom. So this is sigma over 2 epsilon naught, the k-hat direction. And then we still have this sine of z sticking there. All right, so finally, the last part of this says, draw the electric field lines for the infinite square both above and below the plane. Okay, so the electric field is this times the sine of z. So if the plane extends to infinity, but I'll just draw a finite one because I can't draw an infinite one. If you're at positive z, the electric field points up. If you're at negative z, it points down. This is exactly what we found when we did a similar calculation with a charged circle. All right, one part down, 2 parts to go.